Okay, so we have started section 5.3. We have taken a ton of second derivatives, gotten a lot of practice there, just taking second derivatives. So now let's talk about some ways we can interpret second derivatives, and we'll start with a physical example. That physical example is going to be acceleration. So let's say a physical application of the second derivative. Physical here meaning something to do with physics, I suppose, something that tangible, something that we can actually measure. And I'm making a point to say physical application because basically all of the other applications we've done in this class have been with business or finance. Okay, so let's say now, since we have not focused a lot on applying derivatives to physical examples, we haven't talked about physics very much at all. I'm going to start off a little slow with this example and kind of remind you about how we interpret the derivative of a graph of time versus distance. Okay, so let's just get into it. A car starting from a stop. Drives 100 meters in 10 seconds. And comes to a full stop at the 100-meter mark. If you ever look up physics applications of calculus, they're probably all going to be in SI units, not American units, meaning like meters instead of feet and yards, and kilograms instead of pounds, etc. Its distance is a function of time. Its distance can be written as a function of time. Its distance as a function of time is given by capital D of t equals negative 0.2 t cubed plus 3t squared, where d of t is measuring distance in meters and t is obviously in seconds. So I suppose the domain of this function would be, well, it takes 10 seconds to travel, and we're starting at time 0, so 0 to 10 would be the domain of this function. So the graph is given, the graph of this function, which you could actually go graph in your graphing calculator or whatever you use to graph functions. The graph of its distance versus time is, okay, here is the graph. Let's see, I kind of want to center this. Maybe over here. Here's d of t and t. Let's just say 100 meters is here. Let's keep this simple, and 10 seconds is there. So at 10 seconds we're at 100 meters, at 0 seconds we're at 0 meters, and this function is not going to be, it's cubic, right, and it's negative, so we only want it for this little section. It's not going to be a straight line, right? It's going to be something like that. So let's talk about this graph for a second. Just first of all, the shape of it. We're actually going to talk more technically about the shape when we talk about the second derivative, but we can make some inferences about this shape right off the bat here. First of all, you notice that the car is starting off driving kind of slow, right? That's what's happening here. The time, it's taking more time to cover more distance here, so it's driving slow, and then it gets up to speed, and it's driving fairly quickly, we assume, somewhere in here, and then it starts to slow down again, so it can come to a full stop at that 100-meter mark. Okay. What does a point on this graph tell us? A point on this graph tells us the distance the car has traveled in t seconds. So if I wanted to know how far has the car traveled in 5 seconds, I would just say in 5 seconds the car traveled d of 5 is equal to, and you would plug that into your function, and that would be right in the middle, 50 meters. 50 meters. Okay. That's what a point on this graph tells us, and that's how we use the function to find that point. So that's it. This a point on this graph tells us the distance. You plug in time and it gives distance. So this function, so d of t, tells us distance. That's how you get points from a graph. You just take an input value and you plug into the function. That's how you get a point. What does the slope of this graph tell us? The slope What does the slope of the graph tell us? The slope of the graph tells us, well, what is slope, right? Slope is change in y values over change in x values, but that's change in distance divided by change in time. That's speed. That's meters over seconds, meters per second. That's a rate. That's a speed. So the slope of the graph tells us the speed of the car. So if I wanted to know the average rate or the average speed of this car over this whole distance, I would say, well, it traveled 100 meters in 10 seconds, so it's going on average 10 meters per second. But we can be more refined now because we know what a derivative is. We know how to get the slope of some curve at a point, and that's what a derivative is, right? So the slope of the graph tells us the speed of the car. So how do you get the slope of a graph at a point? D prime of t tells us speed. I'll say at time t. Obviously, I feel like that's implied. At time t. So if I wanted to know how fast this car is going at 5 seconds, I could say d prime at 5 is going to, well, actually, sorry, I need d of t first, don't I? I need d of t first. So here's the function. Taking the derivative of this should be fairly simple, especially if you made it through all those other examples. So negative 0.6 t squared plus 6t. That's the derivative of that function. So now I could say d prime. So at 5 seconds, this thing is traveling 15 meters per second. 15 meters per second. So the function itself tells us distance. That's what it was defined as. Its distance as a function is given by d of t. its speed at some point in time is given by the first derivative. Now, what is the next step going to be here? So we know that we can find the speed of the car, say at this moment and at this moment, but these parts of the graph are very different, right? This is where the car is speeding up, this is where the car is slowing down, so we'd like to be able to say more about that. Let me write down what I just said about the shape of that graph at the beginning and end. The curve of the graph tells us, well, the slope of the graph tells us the speed, right? Slope is change in position over change in time, in this case change in distance over change in time. The curve of the graph is going to tell us the change in speed per time, the change in the slope per second. That's acceleration. The curve of the graph tells us the acceleration of the car. How can I say this? Acceleration is speed, change in speed per time. So now we're not talking about a change in distance per time, which we call speed. Now I'm talking about a change in speed per time. Change in speed. So now I'm not measuring the change in its distance per time, I'm now measuring how fast is its speed changing per time. So the curve of the graph is going to tell us that acceleration. And how do we find, if we found the change in distance versus time by taking a first derivative, we want to go, now we have speed here, this is speed, d prime of t. We want to know the change per time in this, we'll just take another derivative. So, second derivative of t tells us acceleration at time t. Acceleration. All of these are at time t, that's implied, it's a function of time. So back here I could have written that here too, so d of t tells us distance at time t. That's implied, but I'll go ahead and write it. Okay, let's get that second derivative. Taking the derivative of this should be fairly easy. It's a polynomial. I'm going to have negative 1.2 t plus 6. So let's see how fast the car is accelerating. Let's see, we've been using 5 seconds. So we know in 5 seconds it is at the 50-meter mark. At 5 seconds it's traveling 15 meters per second. Let's see what its acceleration is at 5 seconds. Let's see. Yes, 0 meters per second squared. That's how you measure acceleration, by the way. Well, at least in these units that I'm using here. It could be feet per second squared or something like that, but it's a distance per time squared. So acceleration, I'll write that off on the side. In general, distance per time squared. In this case, the distance is being measured in meters, time is being measured in seconds. Okay, so how is it 0? What does that mean? Does that mean the car is not moving there? Well, no, because we know its speed is 15 meters per second. This point right in the middle, 0 meters per second, is where the car is, in that exact moment, maintaining a constant speed of 15 meters per second. So if you're going down the highway and you put your cruise control on at 80 miles per hour, your acceleration is 0 because you're not changing your speed. Acceleration measures change in speed. So maybe it would be more interesting to look at this position here, or somewhere earlier in the graph, maybe at 1 second, and then maybe at 9 seconds or 8 seconds. Let's see, let's do that, and let's interpret them. So let's do d double prime, or second derivative, at 1. at 1 second, that would be 4.8 meters per second squared. So we can see at 1 second, when the car is really starting to get going, it's moving, it's accelerating. It has positive acceleration, meaning it's speeding up. So this is speeding up. Okay, what about this part of the graph where it looks like it's slowing down? Now, I picked this function particularly because it's nice and symmetric in this little bound of time. I purposely picked it. You can actually even see, especially in the first derivative, you can really see that there's some symmetry going on here. And when I say symmetry, what I mean is, well, you'll see what I mean in a second. That second derivative at 9 is going to be almost exactly the same, except it's going to be negative 4.8 meters per second squared. So negative 4.8 meters per second squared, so it's actually slowing down because the acceleration is negative here. And it's the same number, it's the 4.8, 4.8, because I specifically picked a very nice function that's symmetrical around in this little bound of 0 to 10. It's, when I say symmetrical, I don't mean completely symmetrical. I suppose that may not be the best word, but what I mean is that the rate that it's speeding up here is the same or opposite, exactly opposite rate that it's slowing down here. And I just picked that because it was easy to deal with. It's a nice, clean example. So at the 9-second mark, this car is slowing down by 4.8 meters per second squared. Okay. Let's see. Pause. Okay. I'm going to work example 1 from the text. It's also an acceleration problem. But they just kind of jumped straight into it, so I wanted to give a bit of a background with this problem. So now that we have that, let's go straight into this example from the text. Let's see, they're measuring something that's falling, and they're doing it in feet per second squared instead of meter per second squared. Okay. So here we go. We have a function for position given by s of t is equal to s naught, that's supposed to be a 0, so a little subscript 0 means you read it as s naught, not meaning like 0 position. Okay, so s of t, this is a position, is equal to this is a function of position for an object that is dropped, not thrown down or anything like that, just dropped from some height. This being the height. And let's just have a little picture here. So we have some object that's falling down, and this would be, well, dropped straight from the edge of the building. This would be, or whatever object this is s naught. And what do we want to know? I'm assuming we just want to know its acceleration. Okay, so find acceleration. Find acceleration of an object dropped from some height. Well, we would say s prime of t. We're going to want a second derivative. If this is a position or a distance function, we're going to want to take its derivative twice to get to acceleration. So we go from distance to speed to acceleration by taking derivatives. So first derivative, that s naught's going to go away because it's constant. I'm going to have negative 32t. That's negative 32t coming from the derivative of this. And then the second derivative then will just be negative 32. And by the way, what is this measuring? This is measuring feet. Measures feet as in distance. S prime of t measures feet per second. And, whoops, S double prime of t measures feet per second squared. So, the acceleration of an object in units of feet and seconds, the acceleration of an object on Earth that's dropped has an acceleration of negative 32 feet per second squared. By the way, this is, well, what else can I say about this? It's negative because it's going down. It's, one of the things you run into in physics is you've got to know what your frame of reference is here. So over here, acceleration was negative because we were slowing down, because of the way I defined the problem. But here, it's negative because the object is actually going down, and we're defining a downward movement as negative. And what else can I say about this? Usually, if you look up acceleration due to gravity on Earth, you're going to see this number. And they're the same, it's just that this is in meters, this is in meters, and this is in feet, but they're roughly the same. And this number actually does change a little bit, depending on how high, how far you are from the surface of the Earth. So it will have very slight variations, for instance, if you're somewhere really low, like close to sea level, or if you're somewhere really high, like on a mountain. Alright, some homework to try for practicing applying second derivatives to acceleration problems. Let's just do these three. There we go.